This video is brought to you by mywayteaching.com.
In this part, let us solve one more simple problem. The statement of the problem is an iron bar L1 is equal to 0.1 meter, A1 is equal to 0.02 meter square, and K1 is equal to 79 watt per mole per Kelvin, and the brass bar L2 is equal to 0.1 meter, A2 is equal to 0.02 meter square, and K2 is equal to 109 watt per mole per Kelvin are soldered end to end, as you can see in the next figure. The free ends of the iron bar and brass are maintained at 373 Kelvin and 273 Kelvin respectively. So obtain the expression and hence compute the temperature of the junction of the two bars and the equivalent thermal conductivity of the compound bar and the heat current through the compound bar. Okay. This is the iron and brass which is soldered. So they have given some of the parameters in the question like L1 and L2 equal to 0.1 meter. A1 is equal to A2 is equal to A, that is equal to 0.02 meters square, and K1 is equal to 79 watt per meter per Kelvin, and K2 is equal to 109 watt per mole per Kelvin, and T1 is equal to 373 and T2 is equal to 273. Okay. Under the steady state condition, the heat current through iron bar is equal to the heat current through the brass bar. So we can say H1 heat through the iron bar is equal to heat to the brass bar, that is equal to H. So we can write it as K1 A1 T1 minus T0 by L1, which is equal to K2 A2 T0 minus T2 by L2. For since we know A1 is equal to A2 is equal to A and L1 is equal to L2 is equal to L. So this equation takes the form so the junction temperature is T0, that will be equal to K1 T1 plus K2 T2 divided by K1 plus K2. Using this equation, the heat current H through the either bar is equal to K1 into A T1 minus T0 L by L, that is K2 A T0 minus T2 by L. So if you simplify this, we get K1 K2 by K1 plus K2 into A T1 minus T0 by L, or in other words A T1 minus T2 L into 1 by K1 plus 1 by K2. Okay. And using these equations, the heat current H through the compound bar of length L1 plus L2, that is equal to 2L, and the equivalent thermal conductivity K of the compound bar are given by H dash is equal to K dash into A T1 minus T2 by 2L, that is equal to H. And here we know K is equal to 2K1 K2 by K1 plus K2. And T0 is equal to K1 T1, as we already found the value of this temperature. We get the value for the first one as 79 into 373 plus 109 into 273 divided by 79 plus 109, which gives the value as 315 Kelvin, isn't it? Similarly, for the second case, that is K dash is equal to 2K1 K2 by K1 plus K2, that is 279 into 109 divided by 79 plus 109, which is equal to 91.6. Okay, this is the solution. And using this K dash, we can find the value of H dash, that is nothing but the equivalent thermal conductivity of the compound bar, that is given by K dash A T1 minus T2 by 2L. Okay. And the third part, the heat current through the compound bar, that is H. 91.6, 0.02 into 373 minus 273, that is 10, that is 100, by 2 into 0.1, which gives 916.1 watt. Okay, these are the solutions for the three parts of the question. Convection. Convection is a mode of heat transfer by actual motion of matter. It is possible only in case of fluids. Okay. Convection can be natural or even it can be forced. In case of that natural convection, gravity plays a very important part. When fluid is heated from below, the hot part expands and therefore it becomes less dense because of buoyancy, and it rises and the upper colder part replaces it. Again it gets heated and that colder part also rises up and replaced by the colder part of the fluid. So this process goes on, and this mode of heat transfer is evidently different from that of conduction. So here it involves bulk transport of different parts of the fluid. In case of forced convection, material is forced to move by a pump or by some other physical means. Very common examples are, the for this forced convection systems are forced air heating systems in home, the human circulatory system, and even you can consider the cooling system of an automobile engine. In the human body, the heart acts as a pump that circulates the blood through different parts of the body, so transferring heat by forced convection and maintaining it at a uniform temperature. So, natural convection is responsible for many similar phenomena. So, during the day, the ground it heats up more quickly than large bodies of water do. This occurs, you know why? Because the water has a greater specific heat, and because mixing currents disperse the absorbed heat throughout the great volume of water. The air in contact with the warm ground is heated by the conduction. It expands, becoming less dense than the surrounding cooler air. As a result, the warm air rises and the other air moves to fill the space, creating a sea breeze near a large body of water. Cooler air descends and a thermal convection cycle is set up, which transports heat away from the land. Even at night, the ground loses its heat more quickly and the water surface is warmer than the land. As a result, the cycle is reversed. As you can see in this particular figure, this is land warmer than water during, okay, and here water warmer than land. This is night and this is day case. So the other example of this natural convection is the steady surface wind on the earth, which is blowing in from the northeast towards the equator, the so called trade wind. So in normal words, we call it as a trade wind. Okay. A reasonable explanation for this trade wind. See, the equatorial and polar regions of the earth receive unequal solar heat. We all agree for this point, isn't it? Air at the Earth's surface near the equator is hot, while the air in the upper atmosphere of the poles is cool. In the absence of any other factor, a convection current would be set up with the air at the equatorial surface rising and moving out towards the poles, because that air near the equatorial temperature it raises in it rises with the temperature, this, and then it moves towards the poles, descending and streaming in towards the equator. So the rotation of the earth, however, modifies this convection current. Because of this, air close to the equator has an eastward speed of 1600 kilometer per hour. Okay, air towards, near the equator, it has a speed of 1600 kilometer per hour, while it is zero close to the poles. As a result, the air descends not at the poles but at 30-degree north latitude. And returns to the equator. We call this one as the trade wind.